Welcome to the second part of this class on Stochastic Optimality Theory. What I'm going to present in this part of the course is the general architecture that is used in Stochastic OT and the implementation that we're interested in this course, which is the so-called gradual learning algorithm. This is the outline of the class. First of all, we're going to cover the differences between a so-called classic OT architecture and a stochastic OT architecture, specifically the one that is used in the GLA. And we will see that the main difference lies in the evaluation component Eval, where also changes to the structure of the supposedly universal constraint set can be observed. This will help us understand how the modified architecture is able to produce different optimal output candidates at different times, and also, and most importantly, how grammar acquisition could work in an OT framework. This graph displays the classic architecture of an OT system that functions on the basis of two main components, a generating component gen and an evaluating component eval. In OT, we assume that every time a linguistic structure is processed, be it in production or perception, there's an underlying linguistic representation, the input, that is fed into the gen component. What gen does is producing a large list, unbound in size actually, of potential output structures to the input. And nevertheless, since we can only produce one output at a time, the OT system's task also consists of filtering the large set of potential output candidates to the point that only one candidate remains, which will be the system's output. The filtering is done by the component eval, a crucial part of which is the set of universal constraints, con. Importantly, while the set of constraints is said to be present in any speaker, the hierarchy of constraints is not universal, and different constraint hierarchies are what effectively bring about cross-linguistic variation, be it between language A and language B, or between two dialects of the same language. In stochastic OT, on the other hand, there are some extra features added to eval that enable the model to account for intra-speaker and inter-speaker variation of the same linguistic system, and that are also the indispensable basis of how learning in this OT architecture occurs. We will see this in the next slides in more detail, but the only thing to note here is that we see that the constraints point to 2 points called S1 and S2, so-called selection points, and are reordered for this instance of candidate evaluation. So we model inter- and inter-speaker variation by changing the constraint hierarchy from one evaluation to the next, the so-called evaluation time. But how is this possible? Well, let's start with the changes to the structure of the constraint set. In classic OT, we can conceive of constraint orderings as strictly ordered rankings, where we could have a constraint in second, first, or third position, for example. And the higher ordered constraints participate more strictly in candidate evaluation. In this hierarchy, that would mean that even if a potential output candidate was perfectly harmonic with C2 and C3, but violates C1, it can never be the optimal candidate, as long as there exists any other candidate that is more harmonic regarding C1. And in this case, it wouldn't even matter if the alternative candidate violates C2 and C3 or not. And this means that constraints in the classic architecture are actually fixed in the adult grammar. In stochastic OT, on the other hand, eval is a continuous scale, on top of which constraints are represented not as individual points, but rather as probability distributions that overlap. This is done by taking a ranking value, which is going to be the mean of the function, and adding noise to it. And noise can be understood as the function's standard deviation, the mean size by which the values of the distribution diverge from the mean ranking value. And since these are probability distributions, what they tell us is how likely the constraint is to assume a specific ranking value at a specific time. So if we want to know the optimal candidate of a stochastic OT grammar, we will have to give a different answer depending on the time that the grammar tries to produce an output. This is what we call evaluation time t, and during each evaluation time t, each constraint function picks out a point from its probability distribution, and that results in a selection point S. If we take this graph as an example, at an evaluation time t, C1 could pick 86 as a selection point, and C2 could pick 88 as a selection point. And even though we see that the function C1 is generally more likely to be higher ranked than the function C2, at this specific evaluation time, C2 will dominate C1, simply because of the fact that selection point S2 is higher than selection point S1. So, while the ranking values are no longer informative enough to tell what will happen at each evaluation time, we can still make predictions about how the grammar will behave. The fact that the ranking value of C1 is higher than the one of C2 tells us that although the order of the constraints can change from one evaluation time to the next, C1 will dominate C2 in the majority of the cases, but not in all cases, which we can conclude by looking at the distance of the ranking values, which are so close to each other that we can see the functions overlap. Therefore, the possibility that C2 will dominate C1, at least sometimes, is very much a given. And this is relevant because we know that in OT, different constraint rankings result in different output candidates. And now let's put this into a formula. The function that describes the probability distribution of a constraint's selection points is actually just the function of a normal distribution, which you can see here. And if we replace the parameters by ones that are specific to OT, like selection point value, ranking value, and noise, we can make more sense of the equation. So what the constraint function tells us is how likely a constraint C is to pick out a selection point S, given its current ranking value R and the constant evaluation noise sigma. And there's something very important to bear in mind when we examine these values more closely. R is the ranking value that, as we will see next, can change after every evaluation time. Sigma, on the other hand, is a constant in this architecture, which means that at the beginning we choose a value that never changes again, and that applies to every constraint function in the universal constraint set. Knowing this is important because it partially answers the question of this next slide. How does stochastic OT learn? Learning a grammar in stochastic OT means moving the constraint functions along the eval scale after every evaluation time t. Moving the function basically means that the constraint is getting a new ranking value r, because as we know, noise is constant and the selection points are random. Considering the information we just learned about the constraint functions, we can simplify this question of how stochastic OT learns by asking how are the ranking values r updated. And this is done by simply adding an update value to every constraint rank Ri after each evaluation time t. This update value is called delta Ri. We obtain the new constraint rank at evaluation time t plus 1 by adding the update value delta Ri for evaluation time t to the current constraint rank Ri at evaluation time t. So for learning to occur, we don't need to keep track of what's happened to the OT system at past evaluation times. The only thing that matters is the current grammar state. And we just accomplished to further simplify the question of OT learning, because now the question is, how do we know what the update values for the constraints are? And this is where the last part of math comes into play. The update value delta Ri for a constraint Ci is calculated by this equation on the top. Delta Ri is equal to epsilon times sine of Ci of L minus Ci of W. And even though this looks slightly complicated, we will see that the idea behind it is quite simple. Epsilon is one of the values that, like sigma before, we have to decide at the beginning of training, and that doesn't change during the training period. It is called plasticity, or learning rate, and can be understood as a factor that controls how far a constraint can move from one evaluation time to the next. L and W are short for loser and winner. In the context of the GLA, loser simply refers to the learner's output, the output of the grammar you're trying to train, and W to the adult's output, or the output of the supposedly proficient speaker. Ci of L and Ci of W then refer to the amount of violation marks that a constraint Ci assigns to those two candidates at evaluation time t respectively. As you can see, these are part of a subtraction, so the learning mechanism of the GLA depends on how much the output of the learner and the output of the target speaker or adult differ from one another. The last part of the function is a function itself. SGN stands for sign function here. And basically what this function does is deciding whether a constraint is going to be updated positively, negatively, or not at all. Let's apply this to an example of a toy grammar that I chose because it is simple enough to demonstrate the mechanisms of stochastic OT without us needing to think about the linguistic detail too much. In the end, if you want to apply the GLA to real empirical data, one of your starting points should be a descriptive generalization anyway. Well, here we got the input no with two O's from the toy grammar, and let's say that two candidates compete for optimality. One candidate no with one O and another candidate no with both O's. This grammar is regulated by a faithfulness constraint maxIO, which assigns a violation mark for every segment of the input that is not in the output. And also the markedness constraint *OO, which assigns a violation mark for every sequence of two O's in the output. Beneath the constraints, you can see their fictional starting values. I randomly chose 100 and 95 as starting values, according to a theoretical assumption that the initial state of an OT grammar is characterized by faithfulness constraints dominating markedness constraints. But this is actually not necessary, so you might as well just put the same starting value for both constraints, because in the end, the algorithm will have to learn the definite or semi-definite ranking values of the target grammar anyway. Now let's assume that this is the current state of the learner's grammar, where maxIO's ranking value is higher than *OO's ranking value. The learner will thus most probably produce candidate B, no, as the optimal candidate because B does not violate the higher ranked constraint max, given that all segments from the input are preserved, which makes it more harmonic than A, which does not do that. Because A violates max by deletion of the second O in order to fulfill the markedness constraint *OO that is ranked lower. Now the learner encounters a piece of data in the world, let's say from an adult, which produces candidate A and not candidate B. So there's a mismatch between what the learner assumes and what the target grammar suggests. This means that the current constraint hierarchy needs an update, and that's what we are going to do now using the formula from the previous slides. Starting with maxIO, the first thing we're going to do is compare the amount of violation marks that candidate W and candidate L have in common or not. W has one violation mark, so Cmax of W is 1, and L has no violation marks, that's why Cmax of L is 0. Next, we subtract Cmax of W from Cmax of L, which results in -1. -1 is negative, so we know beforehand that this constraint needs to be ranked down because it is too strict in the learner's grammar. Having done this, we already have a part of the update function covered. So we replace the subtraction with -1, and what's left is epsilon times the sign of -1. So the next step is figuring out what the sign function does with this value that we just calculated. This is the sign function, and by its shape we can already see that y can only assume three numbers, -1, 0, and 1. On the x-axis, we have the difference of violation marks between L and W, which is the value we just obtained. And if the value is negative, the function outputs -1. If it is positive, it outputs 1. And if L and W happen to have the same amount of violation marks, then the function outputs 0. The sign function is therefore a threshold function, and as we saw a couple of slides ago, it decides if and how a constraint rank is updated. You might ask yourself why we need this function if we already knew that a constraint maxIO is going to be ranked down. And the reason behind this is that it doesn't matter how big the difference in violation marks is between L and W, because the distance that a constraint can travel when moved is defined by the plasticity value we decide before training, and not by the difference of violation marks specifically. If we look at the update function again, we see that we inserted -1 into the sign function, represented by the blue point here. -1 is negative, and for this reason, sign of -1 equals -1. Replacing the sign part of the function, we end up with epsilon times -1. Epsilon is the learning rate or plasticity that we have to decide ourselves. Typically, you would use values like 0.1 or 0.01. In this case, we will stick to the latter, and this is luckily all we need to update the ranking value of the constraint max.io. The update value is added to the previous value, 100, and 100 minus 0.01 equals 99.99. Obviously, you won't have to do the math yourself. And actually, if you did want to know beforehand how a constraint will behave upon encountering a piece of data, you can just use this rule of thumb. Number 1. If L has less violation marks than W, decrease the constraint's ranking value by epsilon. Number 2. If L has more violation marks than W, increase the constraint's ranking value by epsilon. And number 3. If L and W have the same amount of violation marks, do not change the ranking value. And we can quickly apply this to the markedness constraint *00, which hasn't been updated yet. L has more violation marks than W, so we increase the constraint's ranking value by epsilon, in this case 0.01, and we end up with the value 95.01. I want you to remember that this part only describes how learning works in the GLA. The ranking you see here does not necessarily decide which output candidate is produced, because the constraints display evaluation noise, and therefore the selection points have to be picked out before the output candidate can be decided. In summary, we deal with 3 important functions in the GLA: the constraint function, the ranking value function, and the update function. As I said before, you won't need to actually remember them, but a fundamental understanding of those formulas can help you with value decisions that you will have to make for training. First of all, you will have to set a learning rate epsilon, typically 0.01 or 0.1. Also, you need to set evaluation noise, which is typically set to 1. You will also need to decide which ranking values your constraints will have at the beginning of training. You can either follow theoretical assumptions about initial state constraint rankings. You could also not order them at all and give them all the same values, or you could even rank the constraints according to your hypothesis in order to see if after the training period the grammar remains stable. The last parameter that you will need to decide is the amount of learning epochs or evaluation times that you want to train your model for. The needed size partially depends on the value you chose for plasticity and noise, but just bear in mind that shooting too high is more beneficial than too low in this case, so most of the time you should be fine with values ranging from 100,000 to 1 million. This is where the theoretical part of this class ends, and starting from the next class, we will prepare the files necessary for training and also train our own OT grammar using the GLA.